Hi everyone, welcome back to Past Channels. So we are back to our single linked list, and in this video we would like to implement our first concurrent data structure. In the previous video we tried to implement a single linked list in Rust, but it was single threaded. So in this case we would like to look at concurrent data structures as explained in our book, The Art of Multiprocessing. Our first concurrent data structure will be a coarse-grained synchronized linked list. So why we need synchronization? We can imagine the problems that may arise is in terms of memory bugs if we have multiple threads trying to access one data structure without any kind of order or any kind of synchronization or rules. So one of these, an example would be imagining, for example, the add function. So where we try to add elements to our single linked list without synchronization. So imagine two threads or processes trying to add nodes, different nodes to the same linked list. And in this case, we can think about, for example, what would happen if at this line 23, if one thread is trying to set node.next while another is trying to read at line, is it line 14? So anyway, yes, we can think about what's going to happen if someone is trying to read car equals pred.next and someone is trying to set car equals current.next, something like that anyway. So, or someone is trying to set the head, for example. So what if someone is trying to set the head of the list and another one is trying to remove it in another thread? So this kind of creates memory bugs, one of which is data races. So data races would be two threads trying to write to the same memory, for example, or one thread writing the memory while another thread is trying to read it. So this would be a data race. Another challenge would be in C or C++. We can think about challenges such as use after free, as we shall see later in lock-free cases or the ABA problem. But we can imagine one thread freeing a pointer while another thread is still trying to use it. So that requires synchronization. So for coarse-grained synchronization, as the name says, when a thread is trying to access the list, even though the list might have multiple nodes and it might be interested in only a single node, with coarse-grained synchronization, we will be locking the whole list. So regardless of the node we are interested in, we lock the whole list before we can perform any kind of memory access. And other threads will have to wait. So even if, for example, we might be interested in the tail of the list while another thread is interested in the head. So even though these might be different nodes, we are forced to lock the whole list, and that will be coarse-grained synchronization. The advantage to this is the simplicity that we get. So let's dive in. Right, so we shall go back to our code, and previously we had these two. So we shall add a new file, coarse SLL.rs. Let's add this to our main. And all right, so like previously, we are going to create a struct, a node, and it's going to have a key. We agreed that we just keep this simple. Keys will simply be I32, and again, type link. Our link is simply going to be an option wrapping a box, wrapping another node. Okay, let's implement our node as before. I think this part is pretty similar. We could could just get it from the previous. Let's just get it from the previous list we had. We shall say, just come here and let's just copy all this part up to here. I think this makes sense. Okay, and we can say that in this case we can now it's a bit different here because we would like to lock the whole list, so we cannot just use the link here because multiple threads will have to access this head or the whole list. Anyway, since the head will act as, so we want the head to act as the lock in this case. In other words, if a thread can hold on to the head's lock until it finishes all its until it finishes all the operations, then it should be fine. So the challenge here is if we compare Rust to C or C++, we try to think about cases such as locking or synchronization in C, where we would have to lock the code. So in C, C++, we lock the code. In other words, we are responsible for putting the lock and unlocking. Whereas in Rust, we lock the data. In this case, we lock the data. Again, we want to think about the ownership rules. So since Rust dictates that any object must have a single owner, so we have to consider that as well. We shall see how to go about that. But also, we also know that we have if we have mutability, so if we have multiple owners, then only one of them should be able to mutate the object at a given time. So in a single threaded environment, we look at reference counted smart pointer, or we can look at cell or ref cell. But in this case, we'll be looking at mutex, I think, is a good place for us to start. So every thread trying to, just a second. All right, okay, that makes sense. So if a thread is trying to access the list, then they will pass through this mutex. I don't know what's going on. I have to reopen this. I think that's because of the copy. All right. So if a thread is trying to access our linked list, they have to go through the head, and they must access the lock. So if they get the lock, then we are sure that no one else will get that lock until they are done. So it's safe to wrap this around a mutex, and that should work. All right, let's implement our single linked list. Of course, we start with a new function that creates a simple empty list, whereby we shall say the head is simply going to be mutex new none. So we have nothing. Now let's start with add. Compared to the previous list where this had to take a mutable self, in this case it doesn't matter really, because first of all we can't have multiple mutable references. So we want many threads to be able to call add at the same time, and we will just lock them as the moment they enter. So we don't want to make the mistake of locking code like we do in C or C++ or Java. So in this case, we want to lock the data. So let's lock. In this case, let's create a guard which will act as our lock in this case, where we shall say this is self.head dot lock. Unwrap. Okay. Now we can have the rest from here. We shall say is guard.deref mute. Okay, so as long as this guard is not dropped, then this thread will hold the lock, which means no other thread will pass line 36. Okay. So let's see. The implementation from here on is the same as we saw in. Sorry, this is supposed to return true boolean. So the rest is the same. Again, we don't allow, we do not allow duplicates. I think we can just copy from the previous list. Okay. Let me just copy from the previous list, just to save time. So we had our add function, yes, this one. So from here on, everything is the same as before. We shall talk about the head later, but right. Okay, so right, so instead of this being self.head, we can just say God, and that will work. So again, we will catch any thread that tries to access the load. If we win and we lock the list, then this guard will be, this guard, as you can see, remains, its lifetime is, it remains live until we return. So the moment we get the lock, the guard is live, then any other thread that tries to enter this will be stopped trying to acquire the guard. So that should be fine. Right, let's try to write a simple test for this. Okay, so again, now there is another challenge here where we talk about multiple threads having to acquire ownership, to have ownership of the same list, because again, the ownership rules dictate that there must be only one owner at a time. But again, our threads, in this case, we would like them to have ownership, so we will just give them copies. And the way to do this is to have atomic references. Now, an atomic reference, atomically reference counted smart pointers. So there is the reference counted smart pointer for single-threaded environments, which of course will not be thread safe because the reference counter is not atomic. But in the atomically reference counted smart pointers, the reference counters are atomically incremented or decremented, which makes them thread safe. So we will wrap our list around this atomically reference counted smart pointer. And then we shall try to create threads, a list of threads, and then we shall say let's create about 100 threads, and each thread will take a clone of the list. So what goes around here is whenever we call clone, the reference counter will be incremented to keep track of how many owners we have, and when we drop the clone, then the reference counter will be decremented to show that one of the owners has left the chat, and that will help us to keep track of how many owners we have and prevent us from use after free bugs. So here we shall say threads.push, and here we shall say this is thread. I'm interested in this one, spawn. This is going to be move. Okay, we would like the clone to be moved, so let's try to add for J quite a lot of data. Let's add 10,000 in this case, and we try to mix it up. So if I equals 0 or J modulo I is 0, then we should be able to add. And if that is true, let's try to add J. And then let's wait for all the threads. Oh, sorry, there was an error here. Okay, so let's try to wait for all the threads. And after that, let's try to say that first of all, we would like to ensure that, let's try to ensure that all the data has been added by asserting that all this is on the list. So if we try to re-add it, it should return false. Okay, and let's test this, running cargo test. Okay, as you can see, it's a bit slow. One, because we are using more data compared to the single-threaded one, and two, because of that locking, it creates some kind of performance overhead. But it seems like our add function is working fine. So in our next video, we will try to implement the remainder of the functions, that is the contains function and the remove function. For now, let us stop here. Thank you. If you like this video, please like and subscribe to the channel. Thank you very much. See you next time.